Hey, geometry data people. We're going to start investigation 4 today. So lesson 1 in investigation 4 is going to start on page 175. And we're going to be starting by talking about what are called radical expressions. And all radical means is the square root sign. So we're going to be talking about square roots and how to work with them today. So in the warm-up, we did some really basic review of things like the square root of 25 is 5, the square root of 4 is 2, right? Because I think you already know those things. So square root is the inverse of squaring, okay? So if you had 3 squared is 9. It's 3 times 3. Square root just goes the other way and says square root of 9 is 3. In other words, what number squared would give you 9? Okay, so we're going to talk a little bit about some operations with radical expressions, and then I want to talk to you a little bit about factoring radicals. So when we have, say, 2 radical expressions, 2 square roots, like the square root of 25 and the square root of 9, can we just say square root 25 minus square root 9 is the same thing as the square root of 25 minus 9 and group that together? Well, let's see what happens. The square root of 25 is 5 because 5 squared is 25. The square root of 9 is 3. So this means 5 minus 3, which is 2. What happens if we group them together inside the radical, though? What's 25 minus 9? 25 minus 9 is 16. What is the square root of 16? What squared is 16? 4. It is not the same number, okay? So if you have a square root minus another square root, you can't just subtract them inside the radical. It's a completely different number, all right? What about adding? We'll use the same numbers because they're easy. So the square root of 16 is 4. Plus the square root of 9 is 3, so 4 plus 3 is 7. Well, what happens if you add them inside the radical? 16 plus 9 is 25. The square root of 25 is not 7, it's 5. Okay, so you can't add or subtract. You can't group them inside the radical, okay? But what about multiplying and dividing? Let's check those, and then we'll have all the basic operations. Well, the square root of 36 is 6. The square root of 9 is 3. So it's 6 over 3. 6 thirds, 6 divided by 3, and we can simplify that to 2. 36 divided by 9. If we put that inside the radical, that would be the square root of 36 divided by 9 is 4. What is the square root of 4? 2. It is the same number. Okay. All right, so we can divide. If we have 2 radicals that we're dividing, we can divide them inside the radical sign. So let's check multiplication. Square root of 4 is 2 times the square root of 9 is 3. 2 times 3 is 6. What if we multiply them first? 4 times 9 is 36. So that would be the square root of 36. And the square root of 36 is 6. So that is the same also. So we can group multiplication and division inside the radical. Inside the square root sign, okay? You can't do it with adding and subtracting. All right, now I'm going to digress a little bit to going freestyle here. I'm going to ad-lib. This isn't in your book. I'm just going to make up some things here to talk to you about square roots. So we know 3 squared means 3 times 3, and that's 9. So the square root of 9 is the square root of 3 times 3, and here's why I'm showing you this. We know that's 3. We know the square root of 9 is 3. But look, inside the radical, we needed to have 3 times 3. We needed to have 2 factors of 3 inside the square root, and that's what makes a whole 3. So look what happens with the square root of 12. What can we do with the square root of 12? Well, we can say that that's the square root of 4 times 3, which is 12, right? And we just figured out that we can break that up into 2 pieces. Square root of 4 times the square root of 3. And we know the square root of 3 is 2. And we can't do anything with the square root of 3. So it's 2 square roots of 3. Look at another way we could do it. We could factor the 12. 12 is 2 times 6. We can factor the 6 further, and it's 2 times 2 times 3, right? 2 times 6. So now we're looking for pairs of factors. We have a pair of 2's. We have 2 times 2, so that will come out as a whole 2. And the square root of 3, the 3 stays in. There's only one 3. So that stays in. They can only come out when you have a pair of factors because that's a square and that will come out of the square root. So look at 50. Let's think about how we could square root 50. Well, a short way would be to say, well, that's the square root of 2 times 25. And I know 25 is a square, right? That's 2 times 5 times 5. There's my pair of 5's. 5. And the square root of 2. The 2 stays in. There's only one 2. There's not a pair. What if we looked at it a different way? What if we said, well, I know 50 is 10 times 5. So the square root of 50, that's like saying the square root of 10 times the square root of 5. Watch what happens. What's the square root of 10? That's the square root of 2 times 5, right? Times another square root 5. We know because multiplication, we can put them all together. 2 times 5 times 5. There's our pair of 5's, and the answer would be 5 square root 2. So let's look at a number that's a little more complicated. So 48. Let's see if we can get this down to its simplest terms. So how can we factor 48? I'm not sure what all the factors are, but I know 48 is 2 times 24. So I'm just going to start with that. 2 times 24. Well, I can tell that 24 can have a factor. I can break that down into another 2 times 12. Right? 2 times 24 is 2 times, there's my 24, 2 times 12. I can factor down the 12 even farther. 2 times 2 times, what's 12? 2 times 6. I can go one more time. I can factor the 6. 2 times 2 times 2. And what is 6? 2 times 3. All right, these are all very small factors. They don't break down into anything smaller. Those are what's called prime numbers. They have no factors besides themselves. Now I say, there's a pair of 2's. There's another pair of 2's. Okay, so that pair of 2's makes a whole 2. That pair of 2's makes a whole 2. The 3 is still the square root of 3. 2 times 2 times the square root of 3. Final answer, 4 square roots of 3. And I'm done. All right. What if we wanted to divide? Well, 24 is 2 times 12. Divided by the square root of 3. We can factor the 12 some more. We can say that's the square root of 2 times, we already know 12. 2 times 2 times 3, right? We can put it all together. Remember, if it's a division, you can put it all together. 2 times 2 times 2 times 3. Divided by 3. Remember, when you have a fraction, you can divide the same number out of the numerator and denominator. We can divide out a 3 on both sides. And then what have we got? We've got the square root of 2 times 2 times 2. Pair of 2's. 2 square roots 2. Okay, so that's a bunch of different examples, and I wanted to run through those with you because it'll make the next parts of our lesson go a little bit easier. So let's go on now to page 176. And we're going to talk about simplifying radicals. And that, you guys, is a little bit of what I just did with you. Okay, so for example, the square root of 40 is the square root of 4 times the square root of 10. Square root of 4 is 2. Square root's 10. Okay, 4 is what's called a perfect square. And we know what the square root of that number is. Okay, so that is our final answer. That is as simplified as we can get. All right, so let's try a couple of these down at the bottom of the page. Square root of 12. I think I already did that one for you. We can say square root of 4 times square root times 3. Square root of 4 is 2 times the square root of 3. Or we could have broken it down to 2 times 2 times 3 and found a pair of 2's. What about 27, though? Let's think about 27. 27 is 3 times 9. 9 is 3 times 3. So here's what we have. 27 is 3 times 3 times 3. There's a pair of 3's. 3 square roots 3. Okay? One more that's interesting is, look at this one. Square root of 15 times the square root of 6. So let's see what all of our factors are. 15 is 3 times 5. 6 is 2 times 3. And we're multiplying them all together. So 3 times 5 times 2 times 3. Well, look at you guys. Here's a pair of 3's. So that can come out as a whole 3. And what's left inside the square root? The 5 times 2, which means 3 square roots of 10. Okay? And you're finished. You can't do anything more with that. All right? So that was a whirlwind tour through square roots, because we're going to use them now to talk about right triangles. So on page 177, let's go back to our friend Mr. Pythagoras and the Pythagorean theorem. And a squared plus b squared equals c squared. But we are not going to use a calculator and do decimals, all right? We are going to leave things in square root form. So here we have a leg is 2, a leg is 2. We don't know what the hypotenuse is. That's the piece we're trying to solve. So using a squared plus b squared equals c squared, we have 2 squared plus 2 squared equals c squared. 2 squared is 4 plus another 4. So c squared is 8. And we have to square root both sides, and c equals, all right, we want to simplify square root of 8, so let's see how we can factor it. It's 2 times 4, which is 2 times 2 is 8, right? Pair of 2's, so it's going to equal 2 square root 2. One pair of 2's comes out as a whole 2. The other 2 doesn't have a pair, so it has to stay inside the square root. So final answer, our hypotenuse is 2 square roots of 2. All right, let's try one more. A squared plus b squared equals c squared. This time we're missing one of the legs. So we have 8 squared plus b squared equals 12 squared. 8 squared is 64. Is 144. Subtract 64 on both sides, and you get b squared equals 80. Square root. Okay, so b equals, and we have to factor 80. Well, 80 is square root of 4 times 20, but we can factor 20. 4 times 5, look at what we have, a pair of 4's. So 4 square roots 5, final answer. Okay, 4 square roots of 5. Now, a math rule. Sometimes there are math rules. We don't like to have square roots on the bottom of a fraction in the denominator. That's it's like using improper grammar, okay? So there's a really quick trick to that. It sounds fancy, but it's really quick. It's called rationalizing the denominator. A square root is not rational. We have to change it to be a whole number. And it's super easy to do. So here's an example. We have 4 over the square root of 5. We don't like having the square root of 5 in the denominator of that fraction. Look at what we can do. We can multiply it times square root of 5 over the square root of 5 because that's equal to 1, right? Any number over the same number just equals 1, right? Like 2 halves, 10 tenths, right? Now, when we multiply, you just multiply straight across if you remember multiplying fractions. So it's 4 times the square root of 5. But look at what happens on the bottom. It's the square root of 5 times the square root of 5. That makes a whole 5. Now it's cool. Now it's fine. It has a whole number in the denominator. Okay? So let's see if we can practice a couple. What if we have, this is on the next page, 178. What if we have 1 over the square root of 2? We don't want the square root in the denominator. So let's multiply times square root 2 over square root 2. And then you multiply straight across. 1 times the square root of 2 is the square root of 2. But look at the bottom, the denominator. Square root of 2 times square root of 2 makes a whole 2. This is fine. That's a fine way of saying it. Okay? How about 3 over the square root of 10? Well, we don't want a square root of 10 in the denominator times square root 10 over square root 10. Multiply straight across. 3 times square root of 10 over square root 10 times square root 10 makes whole 10. There's your final answer. Okay? And you'll be doing more of those in your whiteboard chat and in your exit ticket. So that's all for today, guys. Bye.